Welcome to Digital Electronics. So far we have been talking about electrical engineering. I'll be talking about classic components like resistors and inductors, diodes, Schottky diodes, Zener diodes, and so on and so forth. But right now it's time to kind of switch and move to the digital electronics, which is another important part of electrical engineering. So first thing first, one of the things this whole thing is based on is binary. So it's going to be very important to learn how to deal with things in binary. I already made a few videos about this in the past, but I felt like it's a good opportunity to have a fresh new jump start with this. So let's start with a few conversions. So what if I ask you what's the equivalent in base 10 of the hexadecimal number 1a. So now if you want to go from this base here, the hexadecimal base of 1a to base 10, which is one we are currently it's commonly used. We're going to do a few things. So our number here is x1a. Now we're going to remember that the base is 16 because it's hexadecimal, and a corresponds to the number 10 in hexadecimal because it gets to all the number from 0 to 9, and then once we get to a, to the capital A, we get 10 in hexadecimal. So what we do is to say, okay, we're going to take the first number here, of the hexadecimal number, which is 1, and we say times the base, which is 16, raised to the power of, in this case, 1. Why 1? Well, because it will be this 1 times 1, this 1 times 0. If we had 3 number, it will be times 2, times 1, times 0, and so on and so forth. So it's the numbers raised to the power of the numbers minus 1. So plus a, which is the second number, times 16, which is the base, raised to the power of, well, minus 1, 1 minus 1 will be 0. But we know 1 times 16 raised to the power of 1 is 1 times 16. And a, as we said, is 10. So 10 times 16 raised to the power of 0. So 1 times 16 is 16 plus 10. 16 raised to the power of 0. Any number raised to the power of 0 is 1. So it's 10 times 1. We have 16 plus 10, 26. So the hexadecimal, so the hex 1a is equal to 26. And we could do that for any other base. For instance, if I ask you what's oct 37 in base 10, so what's the equivalent in base 10 of the number of the oct number 37. In this case, the base is 8 because it's an octal number. So we say base 8. Therefore, we say, okay, we take the first number, which is 3 times the base, so 8, raised to the power of, well, two numbers, so minus 1 is raised to the power of 1, plus the second number, which is 7, times the base, which is 8, of, well, 1 minus 1 is 0, so raised to the power of 0. And we get, again, 3 times a to the power 1 is 8, plus 7 times a to the power 0, any number to the power 0 is 1. So it's 8 times 3, which is 24, plus 7 times 1, which is 7, which gives us 31. So the octal number 37 is equal to 31 in decimal. And as I said, we can do this over and over and over and over and over again for different numbers. The reason why I choose those two is that what I want to do now is to introduce the binary. So what do we do now? Well, first of all, let's count in binary. There are different types of counters, and we will look into those way later on in this course. But the classic sequential counting in binary, for now, we can just think like counting in binary, like so. 0, 0, 0, 0, 0, 1, then the 1 goes here. Okay, will be like 1, because in binary we basically have just 0 and 1. We don't have anything else. It will be like just like when in base 10 you have 9 digits, and then 10 will move to the other one. So plus 1 will be this, plus 1 again, we will have 0, 1, 0. The reason why we would have this in a counting sequence in binary is that when I do 1 plus 0, 0, 1, 1 plus 1, okay, becomes a 0 because we carry 1 to the other value here, and so we get 1, 0. It will be like having a 9 here in base 10 and adding 1 here. You can just put 10 here because we just put 0 and then you carry 1 here, it will be 10. So in this case 0, 1, 0. Then we go on again. If we had 1, we will have 1, 1, 0, 1, 1, because 0 plus 1 will be 1, and 1 plus 0 will be 1. And then again, if we add 1 once again, this one will become a 0, because it will be 1 plus 1, 0, carried to the other one, but this one is also 1, so 1 plus 1 will be a 0 again, and then we're going to go here to this place. So we will have 1, 0, 0. And then finally, if we had another one, here we will have 1, 0, 0 plus 1, so 1, 0, 1. And again, if we add 1 once again, we will get 1, 1, 1. So this is basically how we count in binary. And this is actually extremely important. There are different types of counters which can follow this sequence or other kind of sequences but this is extremely important. Now, what do we do if we wanna say, okay, let's go from decimal to binary? Okay, and you're gonna see why all of this is important in a moment. Now, what if we want to go from decimal to binary? If you want to go from decimal to binary, let's suppose that we have 37 in base 10, and we want to know, find it in base 2. So we want to know the equivalent in base 2, and we have 37 in base 10. Now, what do we do is to divide it by the base and find whether it's just, you know, an integer without any kind of rest, or if it's a fractional number with, you know, point something. So if I do 37 divided by 2, which is the base, I get 18.5. So the number is 1. Okay, so if you get something, you know, just an integer without any dot, any point, and then something, then the number will be 0. If you don't get an integer, then the number is going to be 1. So 18, and we don't totally use the point something when we go to the next step. So 18 divided by 2 is 9. So the number is 0 because we don't have point something. Now 9 divided by 2 is 4.5. So the number is 1 because we have a 0.5. Then we do 4 divided by 2, which is 2. So we have 0. And then we have 2 divided by 2, which is 1. So we have 0 again. And then 1 divided by 2 is 0.5. So the last one is going to be a 1. Okay. So, and we don't go any farther because it will be 0. So we divide it by 2 and we write the numbers. If it has a point something, then it's going to be 1. If it doesn't, then it's going to be a 0. And then we read them in the opposite direction, basically. So we read them upward. So 37 in binary is 100,101. 100,101. So 100,101 is 37 in binary. And we can do that with many other numbers. Now, the thing is, what if we have a negative number? Because, you know, you can do this for any other number, in any other positive number. You divide them, you get, you know, you try to find whether it's actually, there's a point something and it's 1. If it doesn't, it's a 0, and then you read it upward, and you can convert them pretty easy. But what if you have something like a negative number here? Well, this is where things start to get a little bit trickier. Because with negative number in binary, you can't just, you know, do this. You can't stop here. Okay, so I'm gonna add a question now. What if it was negative 37? Well, if it was negative 37, well, the same thing applies, so we can still do this and read and get this number here, but now we have to do something else. In order to convert it to negative, we're going to do a few things. The first one is that we got to invert, well, the first thing, let's just do this. We're going to convert it to 8-bit, which basically means to 8 values in here. So we have 1, 2, 3, 4, 5, 6. We are missing 2 values to convert it to 8-bit. So what do? Well, we take this number, 100,101, and we add 0, 0, 0, 0, 0, 0, and then 2 zeros. Okay, this looks like pretty useless, but it's gonna be actually fine in a second. So we got 0, 0, 1, 0, 0, 1, 0, 1. Okay, just adding in binary, pretty easy. Okay, now we have 8-bit. Now what I want to do, now that I got here, what I can do is to invert. So basically now I'm going to invert all the zeros and they're going to become 1, and all the 1 are going to become zeros. Okay, so 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, 0 becomes a 1, 1 becomes a 0. And then we're going to add 1. So to this, we're going to add 1 and a number which has all the zeros other than that 1 there. Okay. So now if we add 1, what do we get? Well, we get 1 here because it's 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. And 1 plus 0 is 1. Therefore, the number, so negative 37 in binary is 1, 1, 0, 1, 1, 0, 1, 1. And we can do that again over and over again just to exercise and repeat the steps and just get familiar with those steps. Let's just do this, okay? And write all the steps one by one just to focus, okay? So let's do this. What if we want to convert? So what's negative 54? Okay, so what's negative 54 in binary? What's negative 54 in binary? Now, we could do the same thing, okay? So the first thing applies as if it was positive 54. So we would have 54 divided by 2, which is 27. So we get a 0 because we don't have point anything. Now 27 divided by 2 is 13.5. So it's 0.5, therefore we get a 1 because it's point something. It's not an integer. Now 13 divided by 2 is 6.5. So we're still going to get a 1 here because it's 0.5, it's point something. It's not an integer. But now 6 divided by 2 is 3. Therefore, we get a 0 because we don't have point something. Now 3 divided by 2 is 1.5, so we get a 1. And lastly, 1 divided by 2 is 0.5, so we get a 1. And then we read it upward. Therefore, we get 1, 1, 1, 1, 0, 1, 1, 0. So 1, 1, 0, 1, 1, 0. Okay, this was the representation of positive 54 in binary. So we can stop. Now, how many digits do we have? 1, 2, 3, 4, 5, and 6. We want to reach 8-bit. So, in order to reach 8-bit, we've got to add a number with all the zeros and 2 zeros here on the top. So we're going to do this. 0, 0, 0, 0, 0, 0. So right now we are in 6-bit. And we're going to add 2 zeros, so 0, 0. Therefore, I'm going to get 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1, and then 0 and 0. Now we're going to invert, okay? We're going to invert, so zeros are going to become ones, and all the 1 are going to become zeros. So 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, 1 becomes a 0, 0 becomes a 1, 1 becomes a 0, 1 becomes a 0, and 0 becomes a 1. Now, the last thing we're going to do is to add 1 at the end. So a number with all the 0 except for the last digit, which is a 1. 0, 0, 0, 0, 0, 0, 0. Now, 1 plus 1 is, you wanted to write 2, but you can't. For the thing I said before, it will be like having 9 plus 1 in, decimal. So you write 0 because you carry 1. And then you have 0 plus 1 is 1, the 1 carried by this one. Then you have 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1. So, negative 54 in binary is this number here, this 1 1 0 0 1 0 1 0. So 1 1 0 0 1 0 1 0 in base 2. Okay, so this is pretty easy. Now you are going to be tempted to ask, why are we doing this? And I'm going to explain this in the next video. But keep in mind that this binary is going to be really extremely important for all the things that we're going to do within the next few videos.